The research we are presenting is on the improvement of Lake Lorraine eutrophic status using a comprehensive approach. The researchers involved are Jessica Darling, Zach Dahlman, Stephen Levis, and Keely Lofi. Acknowledgements go to Don Hunting, Royal Carson, Lake and Pond Solutions Corporation, Natural Lake Biosciences, and UWW Undergraduate Research Office. Lake eutrophication in Wisconsin is a big problem. Eutrophication is the process in which an excess amount of nutrients is added to the lake, causing a growth of algae that depletes the lake of oxygen. There are many costs associated with eutrophication, like loss in revenue from lack of fishing, recreation, and tourism, with an estimated loss of $2.2 billion annually. The lake we focused on is called Lake Lorraine, and it is surrounded by farmland. Lake Lorraine has been classified as eutrophic for the last 5 years. Lake Lorraine is located in southeast glacial plains of Wisconsin. This area has intensively developed ecological landscapes with rare communities, aquatic features, plants and animals, including the four-toed salamander and grain milkweed. It has lots of large productive marshes and large shallow lakes. Lake Lorraine is 8 miles south of Whitewater in Walworth County. It has an area of 155 acres and is classified as a shallow seepage lake. You can see algae in the top right picture, where it is covering a lot of water surfaces. The majority of land cover around Lake Lorraine is farmland, which largely contribute to the excess nitrogen and phosphorus that cause eutrophication. As you can see on the graph in front of you, agriculture is 66% of the land cover surrounding Lake Lorraine. If you look on the right, you can see this Lake Lorraine is surrounded by agriculture, which is highlighted in yellow. Multi-factor approach for lake improvement has included 2,4-D and aquathol potassium as herbicides for invasive plant species. Most organisms are tolerant to these herbicides. Removal of floating bogs by dragging the bogs on shore. Remove carbon, nitrogen, and phosphorus from the lake itself. The study that we have focused on is the application of Triton sludge reduction pellets, which is currently being used on a trial basis. The last one is assessment of aquatic vegetation by Lake and Pond Solutions Corporation. We are interested in Lake Lorraine based on previous studies indicating high concentrations of phosphorus around the lake. As you can see, we've taken several core samples around the lake itself. The results from this study show that the deeper into the core sample, the less phosphorus there is. On the right shows a graph with the y-axis saying micrograms of phosphorus per gram sample. On the x-axis, we see all the different core samples taken. We can see that phosphorus decreases as the lower in the sample that we get. The exception for this is from core 5, but it is located right by the crop field, which could be a reason for the results.
The question considered for the study includes, does the addition of Triton sludge reduction pellets affect lake sediment and overlying water chemistry? To address this question, we determined locations for our control and treatment areas. 13 acres were used for the treatment site, and sludge reduction pellets were applied over 5 months at 50 pounds an acre. The treatment locations are shown in the red and yellow perimeter on the map. After each application of the sludge reduction pellets, sediment samples were taken and water chemistry was observed from each treatment and control location. On the map below, the control sites are shown in blue and the treatment sites are shown in red. You can see based on the chart that there was not a large difference in the average depth and the range of depth between the control and treatment sites. The differences are small and they should not affect our data. The parameters we measured include temperature, pH, dissolved oxygen, total dissolved solids, conductivity, and sediment depth. These were measured in the field using a YSI meter at each treatment and control site. At each treatment and control site, sediment samples were taken, as well as water samples from the subsurface and 1/4 of a meter from the bottom of the lake. These samples were brought back to the lab at UW-Whitewater, and we tested water chemistry parameters for phosphorus measurements, including total phosphorus and total dissolved phosphorus. We looked at nitrogen measurements, including nitrate and ammonia. We will look at chlorophyll A, total suspended solids, dissolved organic carbon, particulate organic carbon, and for sediment chemistry, we looked at percent organic carbon, phosphorus, and trace metals. The graph on the left shows the total phosphorus in the water samples from the control sites. The x-axis shows the month of sampling, and the y-axis shows the total phosphorus in parts per million. The month of May shows sampling before sludge reduction pellets were added, while the following months are shown 1 week after the sludge reduction pellets were added. The graph shows that in August, the deep water sample had a massive spike in the amount of phosphorus. This could be due to the increased sampling of particulates. Overall, the phosphate levels are similar in the deep water sample and the subsurface sample in the control site, except for August. The graph on the left shows total phosphorus in water samples taken from the treatment sites. As previously stated, the x-axis shows the sampling month, with May having been sampled before the sludge reduction pellets were added. The y-axis shows the total phosphorus in parts per million. The treatment site, unlike the control sites, does not have a massive spike in August. The treatment sites show that between the deep samples and the subsurface samples, that more phosphorus is located within the deep water sample, but it is similar to that of the subsurface samples. The graph below shows surface sediment depth. The x-axis depicts the sample month, while the y-axis shows the percent change from July. The photo on the right shows a sediment core, and you can see the different horizons in the core, as shown here. The top layer of the sediment core is the top layer of sediment that we looked at. There is an accumulation of the top layer of sediment in control locations, while there is a decrease in the top layer of sediment in treatment locations. This is a steady decrease over time, while it is a relatively steady increase over time for control locations. You can see that there's a clear difference in the control and treatment sites regarding surface sediment depth. The graph below shows percent carbon. The x-axis shows sample month, again with May being sampled before sludge reduction pellets were applied, while the following months were sampled after the application of the sludge reduction pellets. The y-axis shows percent carbon relative to May. Again, the control site had an increase in percent carbon in August. This is likely due to lots of sediment deposition occurring. In September and October, the control sites hover between 80 and 90%. The treatment sites steadily decrease in the percent carbon. Our preliminary findings show that there are clear differences between the treatment and control sites regarding the amount of sediment at the top layer and the percent carbon. Sediment phosphorus will be essential in determining if carbon and phosphorus are being mobilized over time, but we need to finish analyses and decide the best way to represent the data. The implications suggest that if the sludge reduction pellets work, that they can be used in larger lakes to decrease the amount of eutrophication, which would stabilize those ecosystems. These are our sources. Thank you for your time.